Alrighty, gang. Good morning. Welcome back to College Algebra, MAC1105. I apologize in advance for the way I sound this morning. I have a bit of a cold or something. I'm not sure, but let's get into it. I know lately things have been a little bit bumpy. We talked about quadratic functions and we talked about linear regression, but we're going to return to our kind of sensible, structured way of doing things today, coming back to quadratic functions. So just to show you really quickly what things are due when, I wanted to make sure that is nice and clear. Here's the system. So we extended this, right, the linear models and regression, to make sure you guys could get that done until today. So that's due today, right? That just came due, along with homework 6 and quiz 2. Homework 7 is also due today. That was the first bit on quadratic functions. So if you need more time on any of those, you need to send me a message. Preferably a Canvas message, because that'll automatically include your course and section number. Today we're going to pick up where that kind of leaves off. We're going to pick up talking more about quadratic functions. Specifically, this guy, which is mostly about like factoring, finding roots. There's this thing called the discriminant that we're going to need to learn about, and we're going to look at some real world problems, right? Mathematical models. And then homework 9 we're also going to do this week, which is more on quadratics, specifically quadratics that don't have any real x-intercepts, quadratics that have complex roots. So we'll be studying complex numbers a little bit, and then we're going to have a quiz. This is all relevant because we're getting close to exam 1. Right, so test 1 is right around the corner. We are finishing the material for test 1 this week, which means test 1 will be next week. So let's come back over here today. I'm going to do more quadratic stuff. Specifically stuff related to homework 8 and homework 9. And then a note. Exam 2 will be, I'm going to say next Thursday. Right, so this Tuesday and Thursday, we're going to finish up the material. Next Tuesday, we can talk a little bit more and maybe do some review. And then next Thursday will be your exam. All right, so test 1 is Thursday. I'll get the date here. Thursday, February 4th. All right, I'll make an announcement on Canvas, but please just be aware. Be aware that this is going to be the day of exam. Sorry, not exam 2, exam 1. Yeah, we haven't had exam 1 yet. I'm sorry, I didn't mean to scare you. Exam 1 will be Thursday, February 4th. All right, and that's going to cover everything up through what we've learned so far. So, you know, functions, domain, range, graphing, increasing, decreasing, then specifically linear functions and all the things we did with those, and quadratic functions and all the things we're going to do. Let's begin today by saying we can recall that quadratic functions which are functions of the form f of x equals ax squared plus bx plus c. We've learned how to write these in a couple of different ways, right? These they have graphs which are parabolic or parabolas. That graph tends to have like this sort of shape. And this point right here, the vertex, we usually call that h comma k. And these can be expressed in vertex form as f of x equals a times x minus h squared plus k, where h and k are these numbers here, right? The numbers that are the coordinates of the vertex. The number a here, the lead coefficient in vertex form, is the same as the lead coefficient in standard form. And then h and k are the coordinates of the vertex. This is the stuff that we've done so far, right? We've talked a lot about vertex form, and we've talked a little bit about the standard form, and we've done a meaningful amount of graphing where we find the axis of symmetry, we find the vertex, or they give us those things maybe, and they ask us to write the thing down in vertex form, all that shit. So basics, right? Background. Today, we will talk about solving quadratic equations. And there's going to be a few methods. So we're going to use the methods of, sometimes you can take square roots, but most of the time you need to factor. So these are the kind of two main attacks. And then there's also this diagnostic tool called the discriminant. But we'll get to that. So here, I'll hold here just for a second in case anybody needs a second to get any of these bits down. When it comes to factoring, our biggest tool here is going to be the AC method. So I'll teach you that. I'll also teach you some other factoring tricks. But before we get there, let's just look at some basic stuff. I also want you thinking about the geometry of the situation. So let's solve the quadratic equation. Let's say 4 minus x squared equals 0. So how do we do this? How do we solve this equation? The simplest thing we can do is say, okay, I'm going to add x squared to both sides. And that will give me 4 equals x squared. And then I can take square roots on both sides. When we do that, we get a plus and a minus. We usually only write the plus and minus on this one side, right? So as to not confuse ourselves, the square root of x squared on the right, we say that's just x. And over here, the square root of 4 is plus and minus 2. So it's okay, my solutions here are plus and minus 2. So this is the method of square roots. The other way we can do this is by factoring. You can take the expression 4 minus x squared equals 0 and factor this. As a difference of squares. So let's just check something. I claim that 4 minus x squared can be rewritten as 2 minus x times 2 plus x. So 4 minus x squared equals 0 is the same as saying all of that is equal to 0. You can check that if you distribute this back out, if you FOIL everything, 2 times 2, that's 4. Then you'd have plus 2x from your outers, minus 2x from your inners, and then minus x squared from your lasts. So this really does factor like that. This is called the difference of squares. And then you can set each of those factors equal to 0 on its own. Now, 2 minus x is equal to 0. You add x to both sides, get 2 equals x. 2 minus x, 2 plus x equals 0. Subtract 2 from both sides, you get x equals negative 2. And you get the same solutions, right? You get x equals positive 2 and x equals negative 2 out as your solutions. So on the left, this is the method of square roots, right? Where you isolate the x squared and you take square roots. On the right is the method of factoring. And this is a particular factoring trick called using the difference of squares. I'm going to show you more general methods for factoring. But before we go into that, I want to talk about which method you can use when, right? So here we used square roots. So when can you use the method of square roots versus the method of factoring? What's special about this particular equation that allows us to use the square roots method? Well, let's look at another problem. Say I want to solve the quadratic equation. Let's go with this guy. Yeah, Mark's kind of on the money there. It's got to do with the terms that show up. So the quadratic equation in the first example here has a constant c and the quadratic term x squared. It doesn't have any x terms. B here is 0. If you look at this guy, this next example, if we try to solve this using square roots, we run into real trouble here. You can isolate the x squared, so you have x squared plus x minus 6 equals 0. You can add 6 to both sides. You get x squared plus x equals 6. And then you can subtract x from both sides. So you get x squared equals 6 minus x. But now if you take square roots, you do get a true statement here. If you take square roots on both sides, you get x equals plus and minus the square root of 6 minus x. But this doesn't help. Because I don't know what to do with this. I don't know what to do with that x under my square root. And the square root of 6 on its own is a nasty number, but you can't, like, there's no nice way to split this up. There's no nice way to solve for this x without having another x trapped over here. And if you solve for this x, you'll have an x trapped over here. So because this has a linear term, a non-zero value of the constant, the coefficient b, we can't solve using square roots. But we can factor this. Lots of people have different ways they like to think about factoring. But the way that always works is the AC method. So if you're really stuck or if you can't see what else to do, the AC method is the trick. What we need to do is multiply A, which is 1, and C, which is negative 6. And then we look for two numbers that multiply to that product and add up to whatever the middle term is here. So in this case, a times c is -6 because a is 1. So I'm looking for two numbers that multiply to -6 and add up to +1. So I need two numbers that multiply to -6 and add to +1. And yeah, these aren't terribly hard to find, right? In this case, there's two integers that do it. Yep. Yeah, -2 times +3, that's definitely -6. And -2 plus +3, that's definitely +1. So we can rewrite this as x squared plus 3x minus 2x minus 6 equals 0. Here I'm showing you the whole AC method. Some people know you can skip through some of these steps if you know how things are going to go, but in general, this is what you do. And then you factor by grouping. So you factor as much as you can out from this group, as much as you can out from this group. And if you chose your numbers correctly, you'll have a common factor between those two after you pull everything out in groups. So from the first group here, I can factor in x, and what's left is x plus 3. From this second group, I can factor out a -2. So this is going to be -2 times, and then what's left here is x plus 3. And all this is still equal to 0. And now what you notice is that the x plus 3 factor is common to both of those terms. So you can pull him out on the right. And what's left will be x minus 2. So when we factor the x plus 3 out on the right, what's left here is x minus 2. So you get x minus 2 times x plus 3 equals 0. And that's it. You factored the thing. This is called the AC method. And generally, if the coefficient of x squared is 1, if the number in front of x squared here is 1, you can skip some of these in between steps and just jump down to this. But if the coefficient of x squared is not 1, if it's something else, then you'll want to go through these steps carefully. All right, so here we find our two solutions again. We set each one of these pieces equal to 0 on its own. And we get the solutions. When we set those pieces equal to 0 on their own, we're using what's called the zero factor property. So I'll hold here for a second. I guess we should say really the first step here is set x minus 2 equal to 0, set x plus 3 equal to 0, and then we get these. I want to go through a couple ways people kind of make mistakes here, a couple common misconceptions, and I also want to show you a more challenging problem before we conclude for the day. But first, are there any questions about this? Like why the square root thing didn't work here? Why can I not solve this taking square roots? Are we clear on that? Like, this cannot be simplified further, sadly. This is not the same as the square root of 6 minus the square root of x. No, there's nothing along those lines that can be done. Square roots hate having addition or subtraction going on inside of them. That's kind of the way to think of it. The square root is a power. Powers don't play nice with addition or subtraction. So there's no nice way to just straight up isolate x here. Solve for the x squared term, you'll have an x trapped under here. If you solve for the x term here, you'll have an x squared over there. Okay, so I'm going to stay on the same example here. Look at a common mistake or two, and then I'm going to talk a little bit about the properties in state at play, and move on. So we still want to solve x squared plus x, right? Minus x plus x. plus x minus 6 equals 0. Oftentimes, I'll see people try to combine the two methods in a way that doesn't really work. Like I'll see somebody go, okay, well, I've got x squared plus x, and I can add the 6 over. That's not incorrect. And then, okay, well, I know how to factor what's here. I can factor this as x times x plus 1 equals 6. And then doing the same sort of thing that we normally do with zeros, they'd say, okay, well, this means that either x is equal to 6, right, setting this guy equal to 6, or x plus 1 is equal to 6. Therefore, here x has to be 6 minus 1, which is 5. And say, okay, well, the solutions are 5 and 6. Can anybody tell me what's wrong with this? There is a logic error here, and I'd like you guys to help me find it. It's not an algebra error, right? The adding the 6 over, factoring all of the algebra there is correct, but there's a logic error somewhere. I'd like you guys to help me identify the mistake. It's true that x cannot simultaneously be 5 and 6, but remember our previous guy, we had two solutions, right? Here we had like 2 and negative 3s solutions, and that was okay. So it's okay to get multiple solutions out. We're not saying that they have to be these values at the same time. We're just saying that either of these would make the original statement true. So it's not the plurality of solutions. That's not the issue. There's something else going on. But I appreciate the bravery to make a conjecture, and I want to hear what everybody has to say. I'd really like us to think hard about this and talk to me a little bit. I see this a lot, so it's something I'd really like to hear your thoughts on. All of you, any of you, everyone, please. Yeah, we're getting at something here. It's not that x should necessarily be 0. If we plug in 0, we get the statement negative 6 equals 0. So 0 isn't a solution. But normally when you do this, right, when you take your factors and set them equal to something, usually that thing is 0, right? Like after you factor, usually you set each factor equal to the thing over here. But the thing over here is always 0. Why is that? So Brooke's pretty close to home here. Does anybody else have any ideas? Really love to hear again, just anything you're thinking. So the logic error is here, right? It's going from this step to this step. This is a theorem called by a few different things. No worries about parens here. No, that's not so much the issue. So the issue is that if you have two things multiplying and they're equal to 0, then it's true that one of those things must be 0. So the statement on the right here is the thing that we use after we factor to set each factor equal to 0. The problem is, if you have two things multiplying to equal 6, nobody said that means one of them has to be 6. There's lots of ways to have x times x plus 1 equals 6 that have nothing to do with x being 6 or x plus 1 being 6. Think about it like this. Here's one chunk, right? The x is one chunk, and this is one chunk. Just because when you multiply two things here, you should get 6 out, does not mean that those have to be 6 on their own. It is true that if you have two things multiplied here, if you have two things multiplied equaling 0, this does mean that one of those factors has to be 0. At least one of those factors has to be 0. The only way to multiply two things and get 0 out is if one of the things is 0, right? I want you to think about this carefully because this is a really common mistake. And if once you understand why it doesn't work, you'll never ever make this mistake again. The only way to get two things to multiply each other and have them equal to 0 is if this one is 0, or this one is 0, or both are 0. And the only thing that's special there is the 0. If I have two things multiplying each other equal to 6, it does not fucking mean that one of them has to be 6. One could be 2, the other could be 3. One could be 6, the other could be 1. One could be 12, the other could be 1/2. But if I have two things multiplying together equal to 0, then one of them has to be 0. The only way to get a product of two numbers to be 0 is if one of them or both of them is 0. So the idea that shit1 times shit2 equals 6 implies shit1 equals 6 or shit2 equals 6. This is fucked up logic. Small pp. Bad logic. But the idea that shit1 times shit2 equals 0 implies that shit1 equals 0 or shit2 equals 0. This is solid logic. Big PP. So it's the 0 that's special. If you got two things multiplying to be 0, right? If you've got some factors multiplying each other and you know that those are equal to 0, meaning like your equation, you've pulled everything to one side so that the other side is 0. After you factor, then you can set those things equal to 0 on their own. This is supposed to be the word or. Sorry, my pen is dying. But if you've got two things multiplying together to equal 6, it is in no way true that one of those things has to be 6. One of them could be 2, the other one could be 3. One of them could be 12, the other one could be 1/2. One of them could be 24, the other one could be 1/4. One of them could be 18, the other one could be 1/3. Right? It's in no way true that the product of two things equaling 6 means one of those things has to be 6. But it is true that if you have a product of two things equaling 0, then one of them must be 0. And this is actually a really deep statement. When you get into higher mathematics, you start studying something called abstract algebra, study number fields in general, or more generalized mathematical objects that aren't necessarily real numbers or complex numbers, other things. This statement that the only way to get 0 out is if one of the two things being multiplied is 0 is a big deal. And it's important even in those more general settings. All right, so this is the magic. It's that you have to have 0 over here in order to play this game. If you've got some factored shit equals 0, then you can set each of those factors equal to 0. If you've got some factored shit equals anything other than 0, you can't do anything with that. There's nothing you can do with that. It's not useful at all. So what's the moral of the story? If you're going to factor, first you need to pull everything over to one side. We never do this, right? Where you go from this to this, pushing that 6 over, useless. I don't care that I know how to factor this because it's equal to 6. Having some factored shit equal to 6 doesn't help me. I need to have a 0 on that right-hand side. All right, so this is the 0 factor rule, 0 factor property. And we'll use it now when we talk about quadratics. We'll use it later when we talk about other polynomials. So a useful thing in general. So I want to solve a handful more problems here, and I've got your homework. So let's look at a handful of trickier ones. I'd also like to talk about the geometric interpretation, and we need to talk about the discriminant as well. So let's do this. Let's look at something a little gnarlier. One. Yeah. All right. Questions on this before I move away from this concept? It's a big deal. Hopefully none of you guys will ever be tempted to do this sort of thing in the future because you'll thoroughly understand why. But if there are any questions about what's going on here, what I'm talking about, I'd love to spend whatever amount of time is necessary to get it clear. All right, moving along. Understanding the geometry of quadratic equations. Look at a couple of examples. I have here a quadratic equation, and the b term is not 0, right? There's an x squared, there's an x, and there's a constant. So if I'm going to solve this, I need to factor, right? I cannot solve this by taking square roots. If I factor on the left, I see I need two numbers that multiply to 1 and add up to 2. So this is going to factor as x plus 1 times x plus 1. And my right-hand side is still 0. We can rewrite this as x plus 1 quantity squared equals 0. And then just setting these factors to 0 on their own, whether you do it from there or from there, your solution x plus 1 equals 0, x equals -1. This fellow only had one solution. And over here, I'm going to draw the graph of the relevant function for you. All right, this is the graph y equals x squared plus 2x plus 1. And the vertex right here is at -1, 0. So this is our y-axis, this is our x-axis. You notice that this quadratic equation only has one solution, unlike the previous two we've seen, which each had two solutions. if we look at a slightly different example, this guy, he doesn't have any x terms. We can try to solve him taking square roots, right? He just has an x squared and a constant. So I can subtract the 1 over. I'll get x squared equals -1, and then I can take square roots. When I take the square root on the left-hand side, and over here I'll get plus and minus square root of -1. Square root of x squared is just x. So this is x equals plus and minus the square root of -1. But the square root of -1 is undefined. At least it's not a real number. We'll talk about these in a minute. But if you think about it, is there any number that when you multiply it by itself, you get -1? Well, a negative times a negative is a positive, and a positive times a positive is a positive. So there's no numbers, no real numbers that you can multiply by themselves to get negative numbers. So there is no real number satisfying square root of -1, right? So this has no real solutions. So this equation has no real solutions. And the corresponding graph here looks like this. And of course, we've seen that quadratics can have two solutions. So here we had one solution. Here we have no solutions. And on the previous page, we saw an example with two solutions. Let me try showing you one more like that so we can kind of think about these guys together. I can take something like zero equals x squared minus 4. And this is the same as 0 equals x minus 2 times x plus 2. That's that difference of squares trick again. So the equation here has a graph. The quadratic here has a graph looking like this. So if we look at these three graphs, here we have no solution, one solution, no solutions, two solutions, namely x equals 2 and x equals -2. Is there a way to tell a priori which case we're in? All right, this guy had no solutions. In other words, here I drew the graphs for you, and we went through the solution process, and we were able to discover, okay, by solving either, yes, there's one solution, two solutions, or no solutions. But wouldn't it be nice if there's some way for me to tell without going through that process? And is there some connection to the geometry of the graphs that could help us understand why there may or may not be solutions? It's a math class, of course, the answer to both those questions is yes. This is where that thing called the discriminant comes in. So, quadratic equations can have no solutions, one solution, or two solutions. If you have two solutions, then it's true that the discriminant, which is this object b squared minus 4ac, will be strictly greater than 0. If you have one solution, then this object b squared minus 4ac will be equal to 0. And if you have no solutions, then it's true that b squared minus 4ac will be negative. And it turns out these are actually if and only if. So not only is it true that if you have no solutions, then this thing is negative, it's also true that if this thing is negative, then you have no solutions. And these all work that way. So if you know that there's two solutions to the corresponding quadratic equation, you can deduce that the discriminant, b squared minus 4ac, must be positive. If you know that the discriminant, b squared minus 4ac, is positive, then you can deduce that there must be two solutions. The types of quadratic equations I'm referring to here are ax squared plus bx plus c equals 0. Right? You got to be in this form in order to apply this rule. And the object, b squared minus 4ac, this is called the discriminant, because it allows us to discriminate, not in the sense of having negative bias about something, but in the sense of being discerning. It tells us something about the equation in question, right? Namely, if this thing is negative, then there are no solutions. If this thing is equal to 0, then there is one solution. And if this thing is positive, then there are two solutions. And you can check that in each of the cases I just drew. If we look up here, a is 1, b is 0, and c is negative 4. So here the discriminant, b squared minus 4ac, this is 0 squared minus 4 times 1 times negative 4, which is positive 16. So the discriminant here is positive. And that corresponds with there being two solutions to the quadratic equation. So this is true in general, and you can do this for any quadratic equation. If you want to know whether or not it has real solutions, I should say no real solution. And here, two real solutions. Then you can compute the discriminant. Now, if you have no real solutions, that means what you have are two complex conjugate solutions. And next time we're going to talk about complex numbers. I'll show you how to find those complex conjugate solutions. Really, next time is all about the quadratic formula. So next time when we meet, I will prove for you the quadratic formula. We're going to go through a proof of the quadratic formula. And then I will show you how to use it and how it connects to this object called the discriminant. You'll also see how it connects to the vertex, which is a surprising and cool geometry thing. The other thing we're going to do next time is solve some more homework problems, specifically the real life problems, the modeling problems. I know people tend to struggle with a little bit. So I'll ask that you guys please sink some real time into the homework, specifically the quadratic functions homework, between now and Thursday. That way you can bring questions to class on Thursday, and I can try to target the problems I solve towards the things you guys want. But that's all for today. I'm going to go ahead and end the lecture here. Are there any burning questions you guys have before we carry on for the day? Okay, then. I will go ahead and end the meeting here. Please bring questions on Thursday. Remember, exam 1 is going to be a week from Thursday. So not this week, but next week on Thursday. Our second class meeting will be the first test. I'll talk more about exactly how to do that when it gets closer, but you want to be preparing for it. All right, take care, have a good morning, and I will see you guys on Thursday.